So the next concept we want to recall is that of the image of a function. So now that we understand the domain and the codomain of a function, our next step in analyzing a function f from x to y is often to determine the set of all possible outputs. It is normally referred to as the image of the function f, or you may also sometimes see people call it the range of the function f. So as a little refresher, let's consider the exponential function, which accepts as input real numbers and outputs real numbers. We know that for every real number y, which is strictly larger than 0, there exists a real number x, which is the natural log of y, such that if I take the exponential of x, that's the same thing as the exponential composed with the logarithm of y. Because those two are inverses of one another, I get y back. This little computation tells us that the image of the exponential function is actually a proper subset of the codomain, which is the set of all real numbers. So the image is all of the numbers strictly bigger than 0, which we represent as the open set 0 to infinity. So now that we've tackled a familiar example, let's think about the image for a matrix transformation. Particularly, let's go back to the matrix A that we took from example 1. So, if we chase the definition, the image of the function t is the set of all vectors b inside of R3, so three-dimensional vectors, for which there exists a vector x, which is four-dimensional, satisfying the equation b equals t of x is equal to a times x. That is to say, the image of our matrix transformation T is exactly the span of the columns of our matrix A. So if we take the row equivalents, then we can see that the image of our matrix transformation T is all of R3. In general, if you're given a set of vectors, v1 through vn in Rm, the image of the matrix transformation T from Rn to Rm, defined by the matrix A, whose columns are v1 through vn, well, this is just the set span of v1 through vn, which is a subset of Rm. So the next interesting object to recall is the preimage of a function. So while you may not have actually encountered this term in the past, you're familiar with the operation. So if we have a function, f from x to y, the preimage of an element y is the set f inverse of y, the set of all x's in x, such that f of x is equal to y. This, of course, is a subset of the domain x. So to give you a familiar example, let's consider the function f, whose domain is the real numbers and whose range is also the real numbers, defined by the mapping f of x equals x squared. So when we ask about the preimage of a real number a, then by chasing the definitions, we're asking for the set f inverse of a, which is defined to be all the real numbers x, such that x squared is equal to a. So this set, of course, depends on the number a. So since our domain is defined to be the set of all real numbers, if a is a negative number, then we know that the preimage of a is necessarily the empty set, because there are no real numbers that square to a negative. The next oddball case is the preimage of 0. The preimage of 0 is necessarily 0 because the only real number that squares to 0 is 0 itself. So we get a single element set. But for all other real numbers, namely the ones that are positive, the preimage is a 2-element set. The principal square root of a, and it's negative. Of course, geometrically speaking, this corresponds to asking about the intersection of a parabola and a horizontal line. So in each of these, we are asking the question, take the line y equals a, find all the points of intersection, and read off their x-coordinates. In the first case, there is no intersection, so there's no x-coordinate to read off. This set is empty. In the second case, the line, being tangent to the parabola, intersects it at its vertex, which is 0, 0. So we read off 0. In the second case, the right-hand point of intersection, that's our principal square root of a, is the x-coordinate, and the left-hand point of intersection, its x-coordinate is the negative. And this is simply because x squared is a nice even function. So now describing the preimage of a vector under a matrix transformation is very similar. For example, let's go back to our matrix transformation from example 1. So we have our matrix A, and our matrix transformation is called T. So we can ask about the preimage of a 3-dimensional vector. So if we want to know what the preimage under T of this 3-dimensional vector B is, we're asking for the set of all vectors x that live inside of R4 so that when we take T and apply it to that vector, we get B. Well, this is the same as the set of all x's in R4, so that a times x is equal to b. But of course, this is an operation we're very familiar with. This is simply solving a linear system. So to get our solutions, all we need to do is write down the augmented matrix, A augmented by B, and ask Sage to row reduce it for us. So now that we have our reduced row echelon form for our augmented matrix, the fact that our fourth column does not contain a pivot tells us that our fourth variable is in fact a free variable. So we are going to call that variable t. So the first line of our reduced row echelon form gives us the first coordinate of our vector. That's going to be 4 minus 3 times our parameter t. The second line gives us our second coordinate. That's -1 plus 2 times our parameter t. And our third line gives us the third coordinate, 2 minus our parameter t. Then we also include our fourth coordinate, which is our free coordinate. That's just the parameter t. So we can allow t to be any real number, which tells us that the preimage of our single vector b, in this case, is a line in 4 space. So to complete our little dictionary here, we note that given a matrix transformation, T from Rn to Rm, defined by a matrix A, the preimage of a vector B is simply the solution space to the linear system Ax is equal to B. If the system Ax equals B is inconsistent, then we simply say that the preimage is the empty set.